Hi, welcome to my final project presentation for the course Software Development for Robotics, which is an ET, an exploration robot, where the goal is to explore an unknown environment using a robot. I am Srinidhi Srinath, and here's a little bit about myself. I'm a mechanical engineer, and I'm currently pursuing a master's in robotics at the University of Maryland, and my interests are in the fields of motion planning and decision making for self-driving vehicles. So here's a little bit about the project. So the project is basically to explore an unknown environment using frontier-based exploration. So the motivation for this project for me was basically my fascination with extraterrestrial rovers, which are being used to explore and map extraterrestrial bodies. For example, the rovers Curiosity and Opportunity are exploring the surface of the Mars and mapping the entire planet. So there are many challenges involved in exploring an unknown environment, and it's a very exciting field to work in. So one of the techniques used to explore an unknown environment is to use frontier-based exploration, where frontiers are basically the points between explored and unexplored space. So for example, in this image, the light gray region is the explored space, and the region with the greenish tinge is the unexplored space. So the frontier points are basically the points on the edge of the explored space and unexplored space. So all of these points are basically the frontier points. So frontiers are basically the centroid of all of the frontier points. So this blue dot is basically the centroid of all of these frontier points, and this blue dot is basically the centroid of centroid of all the frontiers on this line. So basically the goal here is to detect frontier points, cluster them into different sets of frontier points, and then obtain the centroid of each of these clusters, which in turn gives us different frontier points. So the robot will now navigate to the nearest frontier point and then again map the environment to obtain new frontiers. Once it obtains new frontiers, it will navigate to the next nearest frontier, and so on. This happens until there are no frontiers left. That is, the entire space is explored. So a little bit about the development of this project. I used an agile process for developing the software stack, which is basically a ROS package. The entire project spanned for 3 sprints starting 20th November to 16th December. The development process included solo iterative process and test-driven development. So the entire project is on the GitHub repository, which I'll be shortly shown to you. Before that, here is a sample result of the project. So I have created a custom environment, which is basically a closed room with different elements like tables, cardboard boxes, etc. And here in the middle is a TurtleBot, which is basically a differential drive robot, which I used for the exploration. So here to the right is the result of the occupancy grid after the exploration has finished. As you can see here, the probabilities for the occupancy grid has been updated, and the entire space is fairly explored, and there are no unexplored spaces inside the boundary. So here is the GitHub repository for the project. This is basically a ROS package which implements the frontier-based exploration on a TurtleBot. So before cloning this repository, please make sure that you have installed all the dependencies required for this project, which is basically ROS Kinetic on a system with Ubuntu 16.04, and all the TurtleBot packages are required. So please install all the TurtleBot packages, and Gazebo should have a minimum version of 7.0. So and RViz launchers and Moobase are also packages that are required for this execution of the simulation. So please install all the required packages. So the build process basically begins with the creation of a Catkin workspace. I have already created the Catkin workspace, so I will first go to the source directory in the workspace, and then there I'll clone the repository. So now that the repository has been cloned, the Catkin workspace has to be built. So go to the main Catkin repository and do cat make for the build process to start. This will basically build all the executables and the libraries required for the package to execute. Okay, now the package has been successfully built. Let me go ahead and source the workspace. So before showing the simulation, I would like to run some unit tests and ROS tests to make sure that all of the unit tests are working. So please make sure that you source the workspace before you run the command for running the unit tests. So as you can see here, all the unit tests and the ROS tests have passed. The total number of tests were 11 and all of them successfully passed. So I will now go ahead and start the simulation. So to start the simulation, it's just one launch file that has to be launched, which launches all the required nodes and packages. So here we can see that the gazebo is launched, and the ROS and the console for the Explorer node. Let me go ahead and zoom in. As you can see here, the TurtleBot has started rotating. This TurtleBot starts by rotating to gather the information from the environment, and then the frontiers are calculated. So as we can see here in ROS, as the TurtleBot moves and the sensor spans over the space, we can see the occupancy grid map being updated. And the node has been initiated and the map is being initialized as of now. So currently, once the map is initialized, the frontiers are formed. So here the blue markers represent the frontiers, which is basically the centroid of all the frontier points between explored and unexplored space. And I'm using the MoveBase package to send the frontiers as goals to the TurtleBot. So the MoveBase package takes care of the navigation and path planning. So here the TurtleBot was successfully reached the first frontier. Now it is looking for the second closest frontier. So once the TurtleBot moves to a frontier, it again does a 360-degree sweep so as to gather more information regarding the environment, and all the frontiers are recalculated. So as you can see, even in gazebo, the TurtleBot can be seen moving around. Now the TurtleBot is moving. Yeah, as you can see, the TurtleBot is moving in gazebo as well. This will typically take around 10 to 15 minutes because I have given a wait time of 10 seconds each time the robot goes to a frontier, and I have also given a wait time of total time of 20 seconds for the rotation of the TurtleBot for a 360-degree sweep in order to update the information regarding the map. sometimes the TurtleBot won't be able to successfully maneuver towards a frontier because of various reasons. For example, there can be no path found, or frontiers can be detected wrongly. Uh, some false positives do exist. In such cases, I drop that frontier and do not consider it further. Also, one other behavior that you can see here is that there is a jump in the TurtleBot's position with respect to the map. This is because the move base package uses odometry for correction, and therefore odometry is basically being corrected uh, after some instances. So this results in incorrect poses for the TurtleBot. This can be problematic sometimes because as you can see here, it is trying to go to a point through an obstacle. The move base package calculates a path through an obstacle which is not feasible. So in such cases, typically move base package itself does some recovery behaviors, but it is not always guaranteed to be successful. So as you can see here, if the TurtleBot cannot reach the frontier, I say that the TurtleBot could not reach the frontier and I ignore the frontier. As you can see here, there was a correction in the accumulated odometry error, and therefore that resulted an issue with the pose of the robot as with the pose of the map, and therefore there is a slight shift in the position of the robot, and the occupancy grid map will be re-updated and rebuilt for this region, and new frontiers will be created. The TurtleBot in gazebo is at this position, whereas in the occupancy grid map it has reoriented itself with a slight shift to the left. So the entire map is now going to get updated. This is going to probably take a while. As we can see here, due to the reorientation of the robot, due to the correction of the odometry by the move base, the map has completely uh, oriented itself in a different way. However, the exploration is still going on, and the frontiers are being detected within the new oriented map. So the TurtleBot is here. So basically that means that this is the new orientation of the map. So if the frontiers detected are not reachable, I ignore the frontier and I do not consider them in the next iteration as well. So let's say if there are 3 frontiers which are not reachable, and in the first iteration the first one gets ignored, and in the second iteration the second one gets ignored, and in third iteration the third one gets ignored, even though none of the frontiers were reached, the assumption is that they were not reachable because of some error in the occupancy map update, because they are likely points outside the map or points inside the obstacles which are not reachable. So in such cases it is mm, uh, somewhat okay to uh, deem that the exploration is complete. In most cases the exploration will be complete, uh, since the clustering algorithm and the frontier detection the frontier detection algorithm is not always perfect. There is prone to be some false positives existing, so we can safely ignore those false positives and deem that the exploration is complete. So here the node has finished, so none of the remaining frontiers could be visited because the move base could not find a path from the position of the robot to the position of the any of the frontiers, existing frontiers. So all of them have been effectively ignored. As you can see, even though most of the existing frontiers are ignored, the space is fairly well explored. Most of the places are explored, and there are actually no unexplored places except for a bit of space over here, which is effectively outside the map, given that the map reoriented itself due to correction in the odometry error.